But in this next chapter, we are going to move on to parameter estimation. So this is what we did last time. We have our population. I want to know things about my population because that's what's useful for us. It would be useful for me to know things about the UI students, but it would not really be very useful for me to know something about this particular set of 10 students. So last chapter, from the sample that we took, a smaller manageable sample, we tried to establish an approximated normal probability distribution of the sample statistics. We found that from our individual samples, we were able to estimate the probability distributions of the sum of various data points as well as the mean of these various data points. And we can approximate it using a normal distribution. Now, in this chapter, we want to take that one step further, and we want to actually know from that mean over here, like what happens to my mean over my population mean? What values could it have? And in order to do that, we need to use some estimates. So this is terminology. It was mentioned previously in the video as well, but it was not explained in detail. So in order for me to estimate the parameters that I don't know, be it maybe the mean or the variance or the standard deviation of the population, I need an estimator. I would need an estimator. And in order to determine the estimators, then I need to take this estimator from the sample. And then I can use the maximum likelihood method. So here we use the maximum likelihood estimators. So as the video also mentioned previously, actually any statistic could be used to estimate the value of the unknown parameter, for example, theta. So the only thing we know is this unknown parameter theta is valid for the population, and it could be the mean, it could be the standard deviation, I don't know. But if I want to approximate it, I need to use a statistic from the sample. So commonly, arguably, you can use the mean. However, the video also mentioned you could use the mode, and you could also use the median. It is possible to use different statistics to estimate the unknown parameter. And this is called the estimator. So which statistic you use is the estimator. And the observed value of the estimator is called the estimate. Be careful with these two terminologies, the estimator and the estimate. So if I had a population and I took a sample and I said, oh, the sample mean is 3.1. Mean is the estimator and 3.1 is the estimate. So be careful and don't mix up these two. The estimator and the estimate are two different things. And after obtaining the estimator from the sample, I would like to estimate the possible value of whatever parameter I want from the population. And as also mentioned in the video, there are two ways to do that. Either I want a point estimate or I want an exact value of mean, for example. I want to know exactly that the mean GPA of UI students is 3.267, for example. Or I could use an interval estimate in order for me to have a little leeway. Because if I give a point estimate, I can give you an exact number, which is probably maybe useful. However, I most likely will be wrong. There is a large possibility that I'm wrong. So I could use an interval estimate instead, in which I have a lot more confidence. So I could say that, oh, the mean GPA of UI students is somewhere between 2.5 and 3.5. That way, I won't get sued. That's a joke, but basically it's correct. So I'm not making a false statement. It's a little safer for me to say that the mean GPA is between 2.5 and 3.5 because it's more likely for me to be correct than to be wrong. Whereas when I give you a point, a certain number, there's a big possibility that I am wrong. So if I want to give you an interval, obviously I can't just give you any interval I want. Because like in the case of GPA, if I say, oh, the average GPA of UE students is somewhere between 0 and 4. Of course, duh, but I need to use something called a confidence interval. So this interval will give me a limit, either an upper limit only or a bottom limit only, or both. And this is an interval with plausible value. So I can tell you for sure that it's probably somewhere in this interval. However, we can never be 100% certain that the interval is indeed correct and it does indeed contain the parameter. And we also need to construct the confidence interval with high confidence so that my statement would be a lot more convincing and it would carry a lot more weight. So what does that actually mean? Like, how can I declare my confidence? So I need to use something called the alpha. Like, so previously, the video mentioned something like, this is my 95% confidence interval. So if it were 95%, that means my alpha would be 0.05, right? 0.05. Yes, I think so. So with an alpha of 0.05, that would give me a 100, 1 minus 0.05, 100, that's a 1, 0.95, and that is a 95% confidence interval. What does that mean when I say a 95% confidence interval? So in order for me to estimate that, I could take samples so many times. And say, for example, I took 16 in this case. I took 16 different samples from different places. When I was computing GPA, I took 100 students from the law faculty. Then I took 100 students from that live in Depok, and I take another 100 students that came from outside of the Java island, and I took another 100 from Fasilkom, another 100 that are about to graduate. I'm just taking a random, different random samples. So every time I take 100 people, I take the mean, the sample mean, and then I take another sample mean, and so forth and so forth and so forth. So I took it 16 times in this illustration. I know for a fact that the actual population mean is this one, somewhere there. And when I say that 95%, I'm confident, so my 95% confidence interval, it means that from this 16 times that I take a sample, 95% of the time, it will actually intersect that mu. So here it does, here it does, here it does. But in this particular case, it doesn't. So it happens. So when I say that, oh, this is my confidence interval, the mean will be somewhere between this and that with a 95% confidence interval. It does not guarantee that the actual mu is indeed within these limits. It doesn't guarantee it. It would be incorrect for me to give you a 95% confidence interval like this between A and B, for example, and to conclude that there is a 95% chance that it is in the middle of this. No, it's not 95% chance. However, if I were to take multiple ranges in multiple confidence intervals, so every time I have a sample, I construct a confidence interval, 95% of the time, I would indeed intersect the correct mu. So if I were to give you, two options here, so I say that this interpretation of this confidence interval, sorry, this is a typo, confidence interval. So I'm telling you that the population mean is somewhere between 7.28 and 10.72. I'm giving you two options. So I'm telling you that this is a 99% confidence interval. So the first option is to interpret it saying that, oh, okay, the actual mu is within this interval with a probability of 0.99. The second one is if I took repeated samples and a 99% confidence interval, 99% of the time, the intervals would contain the population mean. From my previous explanation, the correct answer is obviously B, because every time you construct a CI, you do not have a guarantee that the real value is indeed contained in it. That's not always. So basically, when you have if you have an estimator, in this case, perhaps X bar of the sample, then you could use it to estimate the confidence interval of the population. And there are different scenarios in which you can compute these confidence intervals. I have tried to summarize it in this slide, and I've also color-coded it for you to more easily navigate the slides that I published on Scale, and which case do you have, which formula do you need to know, you need to use, sorry. So as you see here, we have different options. So this one is a little optional, so I'm going to put asterisks here. You will more likely need to focus more on this one and that one, the two first conditions. This one is just additional information. So basically, you know that if you are studying one population, if you're studying one population, then you can compute the confidence interval for a normal mean if you know the variance of the population, or if you don't know the variance of the population. Next, if you have two normal populations, so population 1 and population 2, you can then compute, you cannot actually compute the actual M1 and the actual M2. However, you can compute M1 minus M2. And there are also two cases, either when the variances are known or when the variances are unknown. And lastly, we're going to cover one special case at the end, which is the sample is obtained from one Bernoulli population. So this is the first one, when I have only one normal population. So one normal population. And from here, I know that I can take samples and I get a sample mean. And from this, I can then compute the confidence interval of mu of the population if I know the variance or if I don't know the variance. So here is the normal mean estimation when the variance is known. Note that what do we have here? We need to use the sample mean. You need to use the Z table or the standard normal random variable table. You need to use the population variance because you're assuming the variance is known. And you need to use the number of sample points you took. And basically what happens is you can either do a two-sided confidence interval. That means you limit it on the left and you limit it on the right. Or you can also have a one-sided upper, like only the bottom limit or only the upper limit. You may ask, if you can compute the two-sided confidence interval, why bother compute the one-sided upper interval or the two-sided or the one-sided upper interval or the one-sided lower interval? Well, the answer is because in some applications, it's better to be correct than precise. So in this case, in some cases, you would like to leave the interpretation open. So you don't want to limit it. So rather you say that it's the only thing that I can tell you for sure is that it's larger than this value here. That way, whatever statement you say is a lot more reliable because it's less likely that you are wrong. This is in some cases. So for an example, you see here that you have this problem here, and you know that suppose a signal has a value of mean, the population mean that we don't know, is transmitted from location A, and the value of the of location A. The value received at location B is normally distributed with a mean mu and a variance 4. We don't know the mu, but we know the variance. So it still falls under this category. Variance is known. And if I know some successive value, so I have a sample here. I have, how many do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9 values that I know. So I know for a fact my n is 9. I know my variance. This is the variance of the population. It's known. My variance is 4. And I can then also use the z table. So since I know, oops, let me see. Okay. So since I know this is the average, sample mean of the sample. So I can compute it using 1, 2, 3, these values. I need to compute it on my own. And I get 9 here. I also know the variance of the population, and I know my n is equal to 9. Note here that you were not given the alpha, right? You're not given the alpha here. So you don't, oh, you are given the alpha here. Sorry, apologies. So you're either given, this one is an alpha of 0.05, and this one would be an alpha of 0.01, right? So you can see here that this would affect the alpha that you are using. So here you note here that this is already computed using the z table. You can check it on your own. And on the other hand, if you have a 99% two-sided confidence interval, then you need to use the alpha of 0.01. One important thing that a lot of times students sometimes miss is that when you are computing a two-sided upper interval, you need to use alpha divided by 2, because you are limiting it on the left hand and the right hand. So that alpha divided by 2 on the left and the alpha divided on 2 on the right comes together and it is alpha. Where when you're doing the one-sided upper interval, you do not need to divide it by 2 because you're not limiting on this side. So the alpha will fall on the left or on the right only. So these are some examples of this case. You can estimate the normal mean when the variance is known. And you also have a case where the variance is unknown. So if previously you had the variance and you could plug it into the equation here, this variance, now you don't know the variance. The one different thing that you now need to do is you no longer can assume a standard normal variable because you don't know the variance. Thus, instead of using the z table, you need to use the t table instead. Remember, if this was a normal random variable, just assume I drew it right. The t variable, if you remember from last week, is still symmetric. It would still follow a normal-like shape, but it would have different heights or different widths and so forth. So instead of assuming that it is normal, you can use a t instead because it's a good approximation to z. Note here that if you use t, you need to know the degrees of freedom. So instead, in addition to using the alpha, and alpha, you also need to use n-1 as the degree of freedom. N is the number of data points you use to compute the sample mean. And instead of using the variance, instead of using the population variance sigma, you use the sample variance S. So this is when it is unknown. This is an additional information if you want to compute the variance. So here you're talking about the mean, right? We're estimating mean, you're estimating mean when the variance is known, mean when the variance is unknown, and this one is estimating the variance of the normal population. The next type of interval estimate is when you have two normal distributions or two normal populations. As I mentioned, when you have two, you can't actually get the exact value of this, you can't. but you can use both in together to estimate mu1 minus mu2. So the difference of means, the difference in means is what you can estimate. Once again, you are given, you can find the correlating equations that will establish the two sigmas that was shown in our video previously. And here you can see that the difference between M1 minus M2 would fall under these two limits. This would also fall in between these two limits. Please note that here it's alpha divided by 2. This is alpha and this is alpha. Please don't forget. And you have some examples as well as the computations that you can follow. So it's just a matter of, you need to translate this into the information you need, and then you can plug it into the correct confidence interval equation. So here is when the variance is known. Here is when the variance is not known. Once again, if you don't know the variance, you cannot use the standard normal random variable. So you use the t distribution instead. So this is the mean difference when the variance is unknown. Here you have another example that you can use to compute the confidence interval. So up until now, we've talked about the normal populations, right? But as you know, sometimes your population is not necessarily normal. So in this case, if you can assume a Bernoulli population, remember in the first section of this lecture, we talked about a Bernoulli population as well, which you can assume if you have a rather small population. So if you have a Bernoulli random variable, you could define the population as items that would fulfill yes, or items that do not fulfill yes. Students that can drive and students that cannot drive. Students with GPA over 3 and students with GPAs under 3, and so forth. And the individual data points would then be a Bernoulli random variable with a certain probability, and the sum or the number of random variables that would fall into that would be a binomial random variable for a certain number of data points. And if you can assume a Bernoulli random variable, you can also estimate the confidence interval of the mean of a Bernoulli population using this equation here. So you can estimate you can also estimate a two-sided confidence interval and a one-sided one as well. Note that here you can use the z-score because if you remember, the normal distribution can actually be used to approximate a binomial random variable.